Moore, who's actually a graduate of Carleton College where I was teaching. And through this interaction with Tom, I got to discover what an amazing teacher he is in relativity, special relativity, and general relativity. He's written some wonderful books on the subject that I think really go to the core of helping you learn these subjects. So when we were just starting to organize this summer school, the first question was, all right, we need someone to teach general relativity. And I said,
Mhm.
Tom Moore. Okay, next. And so it's a real pleasure to present to you Tom Moore, a professor of physics at Pomona College in California. And I think you're going to get a lot out of the general relativity that he's going to present. But more than that, being in a summer school like this, it's not just the hour and a half in this classroom where you're going to
Mhm.
learn. And I think
Mhm.
Tom's going to be giving you
Mhm.
some activities to do, and we have
Mhm.
this wonderful space for all of us to interact and discuss these subjects. So this is just part of the learning process, and we're
Mhm.
going to be teaching throughout the weeks and month. Okay, so
All
welcome.
right. Thank you. Thanks very much. So it's really nice to be invited to present to you all, and I hope I can possibly live up to that introduction. It's going to be a little difficult, but my task in this series, as I understand it, is to review some basic general relativity with you to lead up to a discussion of gravitational waves. And so I'm. This is a kind of a complicated task because when I teach my general relativity course at Pomona College, I spend about 4 times as much time with students as I'm going to spend with you. And now you're all more advanced, so this should go faster. And I've cut a bunch of stuff, so that should help a little bit. But one of the things that I'm asking you is let me know if I'm going too fast, if I'm going too slow. I'd appreciate feedback on that. And actually, I'm curious, how many of you have taken a general relativity course before? So, okay, lots of people, but I also see some people who haven't. And I feel like my responsibility is mostly to the people with the least background. So I hope that the rest of you won't be bored. Uh, but what I intend to do is also approach some of these topics that may be familiar to you from an oblique angle that I think you'll find interesting and useful. And you, in particular, you might find useful if you have the occasion yourself to teach general relativity, as I have for 3 decades now. So the other thing that I will say is that I am a really strong believer in active learning, particularly with regard to this material. And one of the textbooks that Nelson mentioned that I wrote is a general relativity workbook. And I really mean it to be a workbook. One of the things that I strongly believe is that you become really proficient in this topic only when you've worked it through yourself. And in my class, students read from the textbook, do a bunch of exercises before they even come to class, and we spend the entire class time talking about the exercises, answering their questions, and so on. That's not going to work so well in this environment, but nonetheless, about every 10 to 15 minutes or so, we're going to have a break and an exercise to do that I want you to do with each other and talk about things. And that's actually a way for some of you who are more familiar with the subject to help those who aren't so familiar with the subject. So this is going to be an important part of what we do. The other thing I will say about that is that at this URL, I have posted the draft version of everything I'm going to say. And it's all written out, looks like this. And I recommend, particularly if English is a second language for you, that you download those, print them out, follow through, write your handwritten notes on that printout, and that will help you, I think, focus your attention more. You don't have to take extensive notes, but I want you to focus. Particularly, research has shown that if you do handwriting, actual handwriting, that it helps put things in your brain because you have to formulate and crystallize ideas. If you're typing on a computer, you can sort of type whatever the person says, but if you handwrite, you've got to break it down into more basic ideas. So I recommend that, and I hope that that will be helpful for you. Let's see. So what else should I say? Oh, yes. Finally, I'm really open to questions. And part of the activity, the point of the activities that we'll do, is that it'll give you an opportunity to test yourself against the ideas, make sure that you have them, and if you have questions that result from that, I want to hear about them. And as Nelson said, I'm going to be around the whole month, actually. So I'm really anxious to help you sort through the kinds of things you always wanted to figure out about general relativity and gravitational waves. Okay? And at the end of each of these handouts that I suggest that you print out, there are homework problems. Now, I can't make you do homework. I'm not going to give you a grade. But I really recommend that you try your skill against these homework problems. And I am really happy to help you work through them, check your answers, and I think that that's another way that you can strengthen your own skills in this regard. Does that make sense? Any questions so far? Okay, so let me give you an overview of where we're going to go. First of all, I've got 5 sessions with you. This session is going to be an overview of general relativity, a conceptual overview, and we'll review some aspects of special relativity. I'm going to introduce the mathematics of tensors and in the context of special relativity. Then in the next session, we'll go on to general coordinate systems, and we'll look at the tensor mathematics in the context of general coordinate systems. I'm going to introduce the concept of what I call the tensor gradient, and we'll end up by arriving at the geodesic equation that describes how free objects move in a given space-time. The third session will be about the Einstein equation. We're basically going to derive the Einstein equation, quote unquote, and we'll see both in what sense I mean as a derivation and why it's not really a derivation. But it's going to be similar to what the way that I will, quote unquote, derive Maxwell's equations at the end of this session, should we get so far. The fourth session, I plan to talk about solving Einstein's equation. How do you actually come up with solutions to that equation? And I'm going to show you various tricks for doing that and introducing the weak field approximation to general relativity, which is one of those tricks. Okay, and finally, the last session will be all about gravitational waves. everything you ever wanted to know about the basics of gravitational waves. All right? So in this particular session, what I'm going to do is I'm going to begin with a conceptual overview of general relativity. And I should say that this conceptual overview, every single one of you, and sometime in your lifetime, is going to be asked to give a general description of your research to the public. And this is an adaptation of the talk that I usually give. So I'm deliberately trying to be very conceptual here, something that would be accessible to almost anyone who's taken a little bit of physics. Then I'm going to talk about special relativity, and in particular how I teach special relativity, how I've found over the years is effective for teaching special relativity. We'll talk about four vectors, we'll talk about summation convention, we'll talk about tensors, and then if we have time, we'll talk a little bit about Maxwell's equations and how you can derive Maxwell's equations using tensor mathematics. All right, so let's begin with the overview of general relativity. All right, perhaps the defining characteristic of Einstein's thought was that he was able to distill complicated phenomena into simple ideas and principles. So everybody knows that Einstein's special theory of relativity is based on two simple principles, right? Actually, I forgot all about this. So, two very simple principles. The principle of relativity, which says what? Laws of physics are the same in every inertial reference frame, right? Okay? And the second principle is really that Maxwell's equations for electricity and magnetism are laws of that type. In other words, that should be true in every reference frame, which means that the speed of light is frame independent. Okay? Now, Einstein's theory of general relativity is built also on two very simple principles. And if you really sort of pare it back, one principle is what I call the geodesic hypothesis, that free objects in space-time follow geodesics. And the second principle is the principle of coordinate independence, that coordinate systems themselves have no intrinsic physical meaning. And you take those two, and we'll see as this unfolds how that works, how these two principles lead to the theory of general relativity. Now, usually treatments of general relativity start by following Einstein's intellectual trajectory and talk about the equivalence principle as a starting point. But I've found for a number of reasons that that's not a particularly good place to begin, particularly with people that are brand new to the subject. It's kind of tangential to the real issues of general relativity, and it can be misleading too. And you really can't develop some of the ideas of general relativity starting at that place. So I like to begin with the geodesic hypothesis, which is really basically, even Galileo knew the basics of this, which is that objects that are freely falling have the same acceleration, which ultimately means that an object, if you take an object and launch it at a certain velocity in a certain direction, that every object will follow the same trajectory through space-time. And if you think about it, that's a kind of a really different thing from any other field theory, like electricity and magnetism, where if I launch a proton and a neutron and a positron and an electron and a muon along the same trajectory in an electromagnetic field, they'll all end up following quite different trajectories. So this is a unique aspect of the gravitational field. And one could explain that behavior if the gravitational field, in a certain sense, if the trajectory is specified not by the object's interaction with the field, but by space-time itself, as if the trajectory is marked out in space-time. So the object is irrelevant. The path is already there, laid in front of the object. The object simply follows the path marked out in space-time. Well, how in the heck can space-time mark out a path? What kind of a path would that be? And if you think about it, the analogy is, if you think about a curved two-dimensional surface in space, the surface of an apple, or the surface of a globe, the surface of a hat, those represent curved spaces, and there are unique paths on those, defined by those curved spaces. Those paths are geodesics. And a geodesic in that space can be defined either as the extremal distance between 2 points, not necessarily the shortest, but the extremal, and the definition I'm going to use is the straightest possible path on that surface. So great circles on the surface of the Earth are geodesics. And that is a way that a space-time can mark out a unique path that a free object is going to follow. So one of the basic hypotheses of general relativity is that free objects follow geodesics. Free meaning not interacting with anything electromagnetically or strong nuclear force or weak nuclear force, oblivious of everything else except the space-time around them. So that's one of the hypotheses, okay? Now, it's important to notice that this geodesic hypothesis doesn't work in ordinary space. You need space-time to make this work. And to give an example, so I got to remember that I've got to I have this stuff here. So think about launching a ball at about 5 meters a second horizontal component, okay, and it's going to go from point A to point B in space. But I could launch a bullet at 500 meters a second between the same point A and point B. They follow different trajectories. So clearly there is not a unique path between the 2 points in space. And so geodesic hypothesis is not going to work here. On the other hand, if you draw a space-time diagram of those two trajectories, then first of all you see that they're not going from the same point in space-time, that is the same event in space-time to the same initial event in space-time to the same final event. They both start out here at this point in space and this event instant in time, but the ball goes a lot further in time than the bullet does. And they end up at the same spatial point, which I've labeled B here, but the bullet ends up there a lot sooner than the ball does. And so they're really following different curves in space-time. But what's really interesting about those curves, even though they are different, is that their curvature is about the same. If you match that parabola as closely as you can to a circle, the radius of that circle is a light year. Okay? And so in space-time, those two paths are different, but they are curved the same amount, basically, as described by the radius of curvature. And so, and if I were to launch an anvil instead of a ball at the same horizontal velocity from the same position, same angle, it would still follow the same trajectory as the ball. So in space-time, that path is unique, and that's the geodesic path. Does that make sense so far? All right. So, so I actually, what happened here? Yep, no, I'm going to stick with that. Okay. This is, in fact, this hypothesis is what leads to what people call the equivalence principle. If you think about it, what we're basically saying is that free objects follow geodesics, the straightest possible paths that you can have. And if you think about that in the context of frames near the surface of the Earth, we say, well, this frame in this room is an inertial reference frame, right? And I throw a free object and it falls to the floor. And I say, well, wait a minute, that's a free object. Why is it not going in a straight line at a constant velocity? It's an inertial reference frame, right? And of course, in Newtonian physics, we say, oh, well, that's because there's a gravitational force that's pulling it to the floor. All right? But of course, if we were in a freely falling elevator, or safer yet, the International Space Station, and I took a ball and threw it at a constant velocity, it would move, continue to move with a constant velocity. So there are reference frames, even near the surface of the Earth, where objects really do go in straight line trajectories at constant velocity, and those should be the kinds of frames that we call inertial frames. And in particular, in such a frame, the gravitational force entirely disappears. Right? You're all familiar with that. And whereas this frame sitting on the surface of the Earth, the gravitational force doesn't disappear. But that's because this frame is accelerating relative to the inertial frames that would be in our same location. So if we had an inertial frame that was in our location that was dropping down from above, okay, we sitting in the room to a person in that inertial frame would look like we're accelerating upward and getting pressed to the floor because we're accelerating upward relative to the way that geodesics go near the surface of the Earth. Does that make sense? So when I hold something in my hand, take an eraser, I have to hold it in my hand. I have to push up on it. Why do I have to push up on it? Well, that's its geodesic. Okay? I'm accelerating it relative to its geodesic. How do I do that? Well, I push on it. I have to push upward. And in fact, I have to push up on it with a force that's equal to the mass, the inertial mass of the object, times the acceleration I'm giving it relative to the geodesic. Okay? So the force that I have to push up on it is mg. But m is the inertial mass here. And so, among other things, this geodesic hypothesis is telling us that inertial mass and gravitational mass are, of course, the same thing. Because the weight of this object, quote unquote, is the inertial mass times the acceleration that I have to give it to move it off its geodesic. Okay? So, and if you think about it, if I have a force that appears in one reference frame but disappears in another reference frame, what do I call that force? Fictitious, yeah. So gravity is fictitious. At least the force of gravity that we're familiar with is a completely fictitious force. It's an artifact of our choosing to be in one reference frame as opposed to another. So then becomes the question, well, does that make gravity entirely fictitious? I mean, there is a difference being near a planet than not being near a planet. So what can we sort out the difference as really being? Well, let's look at this picture. So here I'm imagining a room that is freely falling near the Earth. And I put 4 balls in the room, and I'm just going to set them at rest. So in the freely falling room, they're just going to float there. And I'm going to do the same thing, but here in a different room in deep space. And let's see if we can figure out what the difference is. So in this particular case, the balls are, let's sort of retreat back into the Newtonian worldview for a moment, which will give us the right answer, even if it doesn't give the right sort of interpretation of the answer. But it gives us what physically happens. And what physically happens is this ball is a little further away from the Earth than the center of mass of the room is. So it's going to fall a little slower. This ball is a little closer, so it's going to fall a little faster. This one is a little bit to the left of the center line of the trajectory of the room, and as it falls directly towards the center of the Earth, it's going to accelerate towards the center of the room, and this ball likewise the other way. So what we see is tidal forces. These are exactly the same forces as create ocean tides on the Earth, and those tidal forces are present in this frame and can be measured, not in this frame. You watch those balls as long as you like, and they're not going to accelerate towards each other. So here is something, yeah, question? Yeah. Yeah, yeah, that's right. Yeah, right, right. Yeah, 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 right. But bear with me a little bit, though, and I think we'll see where why this is a good, useful introduction. Yeah, you're dealing with some very technical issues that are very interesting to resolve. And like I say, this is an adaptation of a talk that I give to the general public, basically, and let's see where it leads, and then we can go from there. But yeah, no, a really interesting issue. Yeah, yeah, absolutely. So this would be a way that empirically you could test whether you're near the Earth or not, or in some very strange kind of environment. But this would be one, and it'd be really interesting to see what the Riemann tensor would be in a case like you're talking about. But we'll get to that. But let's accept this at face value for the moment and say, okay, this is a test that you can do in an inertial reference frame to see whether you're near a gravitational object or not. And if I were to take and plot the world lines of these balls on a space-time diagram with the time axis up, they're starting out at rest, so their separation is fixed, but then they start accelerating towards each other. So they are parallel lines, and a basic axiom of Euclidean geometry is that parallel lines never meet, right? So here we are with parallel, and these are as good as you can get to lines in space-time because they're geodesics. And so these parallel lines, parallel geodesics, are in fact curving towards each other in violation of Euclid's rules of plane geometry. So what does that mean? The space-time is curved, yeah. Okay? And this is actually a way that people can understand, even with little introduction to this subject, it's a way that people can understand what curved space-time means, why that's a useful concept. So basically the task of general relativity is that we are associating gravitation with the real aspect of gravitation, the part of gravitation that you cannot remove by going to a different inertial reference frame. You're associating that with curvature of space-time, and that the paths that free objects follow are geodesic paths. So what you need to do in relativity is link that all up mathematically. And we do that with the Einstein equation. This is a 16-component object called the Einstein tensor. It's a 4x4 matrix, you can think about it that way, that describes the curvature of space-time. And the equation connects that, this is a constant, to the presence and flow of matter and energy. So curvature linked to matter and energy. Then you have the geodesic equation, and I'm going to talk about the various terms in that next time. But those two equations provide the foundations of general relativity. This expresses the geodesic hypothesis. This says how space-time gets curved by the presence of matter and energy. And that can be nicely summarized by this phrase from Wheeler, which you may have encountered before. Space-time tells matter how to move. That's the geodesic equation. Matter tells space-time how to curve. That's the Einstein equation. That's it. That's all of general relativity, really. The rest is just sort of details. Now, the details are long and complicated, and it'll take us the entire rest of the time to go over. But nonetheless, don't let anybody get away with saying that general relativity is complicated. It's not. It's really, really simple. That's what's so beautiful about what Einstein was able to do. It's so simple. Now, contrast that with, say, quantum field theory or even ordinary quantum mechanics. When I wrote up a textbook trying to do some axioms for ordinary quantum mechanics, I had 7 different axioms, and they were very complicated, strange axioms, things about Hilbert space and stuff like that. This is easy. This is really straightforward. This is why I'm really enthusiastic about general relativity. It's so beautiful. Okay. All right. Any other questions about that so far? So if you want a sort of a more fleshed out version of that, you could look at my textbook on general relativity, where this is basically chapter 1. Okay. So let's talk then a little bit about special relativity. A typical, I don't know what kind of background you have in special relativity, but I know what a typical background is, at least in America. You'll start with the two rules that I gave you. Let's see. You start with the two rules that I gave you, the principles of relativity and the speed of light. And then you talk about time dilation and length contraction. And you derive the Lorentz transformation. And then you go on from there. Does that sound familiar, roughly? Okay. I'm going to propose a completely different way of looking at it, which I've found much more helpful for students learning special relativity, particularly if they're on a journey towards general relativity. And there are some real flaws with the typical kind of presentation pedagogically in terms of, because it tends to lead people in bad directions mentally. In particular, one starts to think that somehow motion affects clocks because clocks slow down when they're moving. And that's a totally wrong way of looking at it, and it leads to all those paradoxes that have compounded the literature. So I suggest instead, and I found this very effective with students at all levels, to start with what I call a geometric analogy. So if you think about, here are 2 points in space. So this is an ordinary two-dimensional space. And if you think about it, I can characterize how those points in space are separated in 3 fundamentally different ways. I can project the positions onto the axis of some coordinate system and talk about their delta y separation or their delta x separation. I can talk about the distance measured along a path length, I'm calling that delta L. Or I can talk about the straight line distance between those 2 points, delta D. Now, is it confusing that those 3 ways of measuring the separation of 2 points should be different? No, everybody knows this. Of course they're different. Obviously, they're different. We're measuring those distances, if you like, variations of distances, in different ways. And then in particular, I could measure these 2 distances, this distance or this distance, with a tape measure. I just stretch a tape measure that goes between the 2 points, read off what it says. So whatever coordinate system I would use, the answers that I get for this distance or for this distance are going to be frame independent. They don't depend on one's choice of reference frame. It's this projection operation where I take and decide how much more in the y direction point B is than point A, and I have to project it back. So I have to decide that this point is the same as this point in terms of its vertical coordinate. That operation is, of course, going to depend on how you choose your reference frames, right? The projections will be different in a different reference frame. If I tilt it, I project it differently, I get different results. So what I'm saying is nobody is surprised by any of this. This is all basic trigonometry fundamentally. Okay? So the thing is that space-time is exactly the same. It's not. So here I've got an event in space-time, an occurrence, some physical incident that occurs at a specific time and place, and another event, and I can measure the separation of those events in three fundamentally different ways. I can project them on a coordinate system, which changes if I'm in a different inertial reference frame, or I can send a clock along a certain trajectory in space-time and look at what the clock says at the beginning and look at what it says at the end. Or I can send it along a geodesic world line, an inertial world line, and see what it says at the beginning and at the end. Should we be surprised that those give three different numbers? No, we're measuring them in different ways. Why would we ever think that they would be the same in the beginning? Well, we would think about it because we have experienced that way, but that's basically because we can only go so fast in the world of our experience that we've never really experienced the difference between that and that and that. But conceptually, this really helps focus the issue that the reason that those times are different is not because somehow, I mean, to say that the moving clock runs slow is as absurd as saying that a curved tape measure has its markings shrink. Who would think such a thing? No, this is physically longer. This path in space-time is physically shorter. It's not about moving clocks or not moving clocks. It's about how you measure it. And that conceptual distinction, I think, really helps people sort through a lot of confusion that might otherwise happen. Does that make some sense? So you begin, and you can see that because if I send a clock along this world line and I'm looking at the clock, it says one time at the beginning and one time at the end. Everybody sees that. You see it, I see it, we all agree. That's what the clock says. So this is a frame-independent number. It doesn't matter what frame we're in. We look at the clock, we see what the clock says, everybody agrees. We look at this clock, we all agree, yep, that's an inertial clock. This is what it said at the beginning, this is what it said at the end. That's a frame-independent number. And in fact, it's an even more unique frame-independent number than this one, because this one could vary depending on the path that I chose, but everybody agrees that there's only one inertial path, one geodesic path between those two events, and that clock is following it. And so that interval, which I'm calling the space-time interval, is an especially important number. Everybody agrees. This number, which is the proper time along that path, depends on the path, but it's also frame independent. This is coordinate time between the events. That depends on your choice of reference frame, because it amounts to a decision about whether this event is simultaneous with that event or that event. And that, because of the way you set up clocks and synchronize clocks, consistent with the speed of light being a constant, if you analyze how you do that, you get different numbers. And I'm not going to rehearse that. I think you're probably familiar with that more or less. Okay? So the real key to understanding what's going on here is to focus on what is absolute. And in fact, I think the theories of special and general relativity are totally misnamed. Historically, of course, what was exciting to everybody was that time turns out to be relative. Well, and looked at it this way, duh. I mean, of course time is relative. It's just as these different ways of measuring distance are relative. what's really interesting is what's absolute, not what's relative. What is physics beyond the reference frame? What can you count on as being physically true? And the most straightforward number, physically true number, is that space-time interval between the two events. So in space, we use the Pythagorean theorem. The distance between 2 points in space, according to the Pythagorean theorem, in any reference frame, I can calculate this coordinate difference and this coordinate difference, and if I square them and add them, then I get the number that is unique and special, the true distance between those points. And if I do it in a different reference frame, same process, I get the same number. Okay? And in space-time, it's similar. The space-time interval between the two events, you calculate it in one reference frame by taking the time interval between the events measured in that frame, subtract the square of the space separations, and you get a number that everybody agrees on. You do the same calculation in a different reference frame, you get something that everybody agrees on. And this is the metric equation, and this is the core of both special and general relativity. And it's the core because it uniquely connects what is relative, this stuff, with what is absolute, this. And it's hard to emphasize the importance of that too much. Okay? So, we can calculate the proper time along a world line by dividing the world line up into tiny steps and doing each step really and then adding up the results. So this is the metric equation for each step, and then all I'm doing here is pulling out the dt right out and back, and then this are the components of the ordinary velocity. So if I know the ordinary speed of the object in any frame, I can calculate the space-time interval. Okay? So, I'm sorry, this is the proper time along that path. So if I know v as a function of t, I can do this integral in principle and calculate the proper time as measured along. And that's exactly the same thing you do in ordinary space. So there's no difference there. And because the space-time interval is frame independent, it turns out that if you think about it, because of this minus sign here, I can get various different signs. It depends on how big the time part is compared to the spatial part. But since everybody agrees on the value of this, everybody will agree on the sign. And so you can classify space-time intervals into three categories. Time-like if the time part is dominating. Space-like if the space-like part is dominating. Whoop, that's supposed to say light-like if they're equal. Okay. And I should also say that it's conventional in general relativity to talk about the space-time separation, which is, if you talk about the space-time interval, sorry, if I talk about the space-time interval here, then I would have the minus signs here, and this would be a plus sign, and that is a positive quantity when time dominates. So when I have a time-like interval. But it's most authors in general relativity use the space-time, what I call the space-time separation, instead of the space-time interval, which is the same thing except the signs are reversed. And in fact, a lot of people use the same word for both concepts. I try to keep them separate this way. Okay? So this is the same thing as the space-time interval squared, just negative. And if you're going to do it in terms of space-time separation, then if space-time separation smaller than 0, then we're talking about time-like. It's space-like if it's, and this still should be light-like. Okay, so that's a summary of what I think are sort of the most important ideas in special relativity to get at this point. And I'd like to do an exercise for you. This is supposed to happen sooner, but so what I've got is little cards like this. And I want you to pass them around. Take one for every 2 or 3 of you. And work on this. Talk with your neighbor about what I've got here. Let's see if we can get these. Okay. So yeah, I've got 25 of them, so it's probably going to be like. Okay. You, any, here. Okay. Who needs? More than enough. All right, good. Oh boy. Okay. So when you've had a chance to read it, talk about it with your partners. Try to come up with some kind of agreement. Don't write on the sheets, but what we'll do is when you're all ready, I want you to hold up this thing and point to the answer with your finger on the answer that you've agreed for the various questions. All right? So let's try and come up with this in 5 minutes if we can. All right? Well, usually I have these in the book, and I just turn, yeah. Uh-huh. Yes, yes. Sorry. Uh-huh. Yes, yes. That's okay. Uh, okay. Let's. I realize that you're all still in discussion, but I want to have some time for the rest of the talk. So let's give a stab at this. So what I'm going to do is for each of the questions, I'm going to ask you to point at the answer, and if there are two answers, point at both of them. Uh, okay. So, or if there are three answers, you've got three people, maybe you figure out a way to do it. All right. So, who measures coordinate time, a coordinate time between these two events? So, what do you think? I'm seeing, okay, I'm seeing, yeah. I'm seeing B and C. I'm seeing A, B, and C. I'm seeing, I think some A and B. Yeah. Yeah. I forgot to say what Z is about. Z is I have no idea. I've been asleep. Okay. All right. So, yeah, so let's talk about this. How do you decide what's coordinate time? Who measures coordinate time? Uh, well, coordinate time means you have a coordinate system. So that means you have an inertial reference frame, right? Yes, statement was bold in the context. I should sub and say in the context of special relativity. We can only synchronize clocks in an inertial reference frame, and so if you're going to decide a coordinate time, yeah. So Alice is out. Yes, that's exactly it. But Bob is in an inertial reference frame, pseudo-inertial reference frame, if we're ignoring gravity, and Kara and Dave are on the train, which is also an inertial reference frame in this category. Does that make sense? Okay, so who measures proper time? What do you have to do to measure? Well, who measures proper time? Show me. Okay, okay. I'm seeing some A and some B, and some people saying both. Yeah, and this is, I haven't defined these terms too carefully, but proper time means time measured by one clock that's present at both events. And space-time interval is a subcategory of proper time. It's a special case where the path that you're following is an inertial path. Other people following non-inertial paths will measure different kinds of proper time. So obviously Kara and Dave are not individually present at each event. Their time depends on the synchronization of their clocks in their reference frame. That's not proper time. Proper time is being present. Okay? And so A and B, because Alice and Bob are both present at those events, they measure different proper times. Who measures space-time interval? Show me. Space-time interval is a special proper time, which, yeah, B. B is right. Good. Bob is present at both events and is inertial. That's proper time. Okay? Who measures the shortest time interval between these? This is actually a little hard. It follows from what I've said, but I haven't spelled out how that goes at all. Who do you think? Just tell me. Okay. Alice, yes. Alice measures the shortest time between those events. Bob, and it's just the reverse of the way it works in ordinary plane geometry. In ordinary plane geometry, a path between 2 points, it's not a straight line path, is longer. But in space-time, it's just the opposite. A path that's not inertial between two events is the shortest path. The space-time interval is longer than any other proper time. It's the extremal proper time path. And that's one way of defining what a geodesic is. Okay? Who measures the longest time? Did anybody figure this out? Yeah, this is why a lot of people are saying B, but it's not. It's C. Okay? And let me tell you why. Let me tell you why. Because the space-time interval, which is what, the space-time interval, which is what Bob is measuring, is equal to delta t in a given reference frame minus delta x squared in a given reference frame. So let's think about Kara and Dave's reference frame. Is their delta t going to be longer or shorter than Bob's delta tau. Longer, because there's a distance between those events in their frame. So coordinate time is always the longest time between, it's always longer than the space-time interval. Other proper times are always shorter. So you always have this relationship, which is useful to keep in mind. So delta tau squared is in the middle, and it's less than delta t squared, but in turn is bigger than delta tau squared along any, forget the squares. It's like that, okay? And that's a useful, and here a lot of you were probably sidetracked by the idea that Kara and Bob are on a moving train, and moving clocks run slow, right? No, no. It's how you measure the interval that's important. And yes, their individual clocks are running slower, but their difference between clocks, what they call simultaneous, is also different, and it actually leads to a greater number in this case because of this. And this is why, this is an illustration of why I think this geometric analogy is so important. It helps you keep straight precisely these kinds of things. Questions about that? Okay, so I'm way behind here, but let's keep pressing forward as far as I can go here. Yeah, question. Yeah, so good question. Yeah, how do we synchronize clocks in an inertial reference frame? There are actually multiple different ways to do it that are all physically equivalent, but the way that's usually talked about in a book, and also I'm going to use a similar example when we talk about Schwarzschild spacetimes later, is to exchange light signals. So Kara and Bob are communicating. They have walkie-talkies or something like that, or cell phones these days. So they have cell phones, and Kara says, okay, I'm going to send a light signal to you, and I'm sending it right now at noon. And the signal goes to Dave, and he says, okay, great, I've got the signal at 1 microsecond after noon, and I'm going to send it back to you. And Kara gets it back, and it's 2 microseconds after noon. And now they know that their clocks are synchronized because it's taken the same travel time to go both ways. And if it were different, then they would say, oh, I guess our clocks are not synchronized. All right? Does that make sense? So, the good question, though. And that exactly is what leads to the problem of when you decide that events are simultaneous or not. So Kara and Dave agree that when Dave receives the signal that Kara sent, that the time that both their clocks should register is 1 microsecond after noon. And they've agreed that those two events are simultaneous. But if you're looking at that same sequence, you'll say, no, your clocks are not synchronized at all because it took the signal a lot longer to go one way than it did to go the other way. And so you'll say, Kara and Bob disagree. So if Bob is watching this, Bob will say, you're crazy. Those events aren't synchronized. But that's as stupid as arguing about whether this point on space is directly north-south of that point on space. Well, it depends on what you think north-south is. Are you using magnetic north, or are you using geographic north, or what? There's no right answer to that. So there's no one true synchronization. All right? Other Anything else before I go on? Okay. I'm going to clip through some of this. This will be a little bit more familiar to you, I think, than some of this other stuff. So, Lorentz transformation equations. We know how to transform coordinates from one to the other. And the fact that I've got a minus sign here and a plus sign here really talks about the fact that these frames are physically equivalent. It's just that I have defined beta is by definition the x velocity of the primed frame with regard to the unprimed frame. So if I switch that definition, I would get a minus sign. Okay, and I can write that in a matrix form like this. And I could write these four equations in a nice compact way this way, where I'm putting these are just indices. They're not powers or anything like that. They're just indices. I'm putting them in a superscript position for reasons that will become clearer as we go on. But for right now, just keep in mind that these are indices. And so mu or nu can range over the four values of the index. And so I can write this equation like this. I can write this equation like this. And in fact, if I use the Einstein summation convention, which is what? What does the Einstein summation convention say? Yeah, sum over repeated indices if one is in a lower position and one is in an upper position. And we'll see why that's important in a sec. But I can write, forget the summation symbol then, I can write this nice and compactly that way. And then if I talk about differences, coordinate differences, since the Lorentz transformation is linear, I can talk about the transformation of coordinate differences that way. So this would be components of a displacement in space-time, like a displacement vector in ordinary 3 space, except you've got an additional time element, right? And then, so I can rewrite the Lorentz transformation equations in this kind of matrix notation like this. And, but then this is, I'm talking about here that the fact that I've got an inverse relationship here. This is really the matrix inverse of this, if you work it out. And they've got to be because they're inverse transformations. Okay, and part of the beauty, though, is that this equation is much more compact than the equivalent matrix notations. And the index notation also provides you the ability to specify sums in a more flexible way than matrix notation does. And that flexibility becomes really important as we go to general relativity. Okay? And we can write the metric equation in that nice compact notation. If we define a metric tensor, this is a metric tensor. It's just a minus up here, plus is down here, diagonal otherwise. Then this gives the space-time separation in that compact notation. And I'm doing a double sum here, right? Or a sum over mu, a sum over nu. Same thing. Now you might think, well, wait, that's overkill for this simple equation. Yeah, it is. But not in general relativity, it's not. This is the key to going forward, okay? And so I can define a 4 vector. I've already got the transformation law for a 4 displacement, that is, the ordinary Lorentz transformation. So I'm going to define a 4 vector to be to transform in the same way as the displacement. And that's really the way you define any vector in ordinary space. When I say that the object's velocity is that way, what I mean is that its components transform in the same way that the components of my arm displacement transform. So if you look at it at a different coordinate system, you still agree that those are parallel. So, and I can define the magnitude of that vector, if you like, the dot product of the vector with itself, by doing the same thing I did with the for displacement to get the invariant space-time interval. And because the invariant space-time interval is frame independent, this will be frame independent too, because it's transforming the same way. Okay? So, and by the way, this kind of bold sans serif notation is typical for four vectors and other tensor quantities in the literature. One of the most important four vectors that we have is the four velocity, which is defined to be a differential displacement divided by, you're sort of imagining an object following a world line. It's the differential displacement along that world line divided by the object's own proper time. Now this is frame independent, and this is just a displacement. So how does the four velocity transform? It transforms as the numerator transforms. So it's a four vector. And this four velocity, which is going to come up over and over and over in what we do following, is a very important vector. Its magnitude, following this sequence of logic, so this is the definition of what I mean by the squared magnitude of the four velocity. And I'm plugging in what the definition is. Oh, forgot to change that to new, and did it over here. And so I've just pulled the metric tensor up here, but this is the definition of the negative squared space-time interval along that differential displacement, which is the same as the denominator, so -1. The four velocity of an object, no matter how fast it's going, is -1. Okay? And another important vector is the four momentum, which is defined to be the mass of the object, which is invariant, times the four velocity. And so its components are simply this, and its squared magnitude is just negative the mass squared. So in fact, that's the way we define mass in special relativity these days, is the negative squared magnitude of the for momentum. It gives you mass squared, I should say. Okay, so and so we can go from that, whoops. Oh yeah, I've skipped over this. If you want to find the time component of the four velocity, it's the coordinate time over the proper time, which we showed on an earlier slide. The proper time is dt times the square root factor for a differential displacement. And so your ratio is just 1 over that square root of 1 minus v squared. And your x components are the ordinary velocities, dx over dt, times that square root as well in the denominator. All right, so those are for velocity and for momentum in special relativity. Now let's talk about gradients. So here I've got, imagine I have a scalar function. So this is a function of t, x, y, and z. And I want to take its derivative. What kind of an object do I get? Well, what am I doing here? What's that rule in calculus? Chain rule. Okay, so I'm just doing the chain rule, but that component is the time-time component of the inverse Lorentz transformation. It's basically, if you look at how I get t from t prime, that's the inverse transformation. And so this particular one is the time-time component of that. And similarly for these other components. So it's transforming sort of like a 4-vector, but not quite like a 4-vector, because what's the difference? Yeah, I'm using the inverse Lorentz transformation here, not the forward Lorentz transformation. So a 4-vector would have a lambda here, not a lambda minus 1. Right? Did I do it? Oh, yes, totally is. Sorry. So this should have been t prime down here, yes. T prime, and the x should have been here. Thank you. Sorry, total garbage. Looked good though. All right. Yes, thank you for catching that. Appreciate that. Okay. Yeah, so this one was right. X, X, Y, Y, Z, Z, T prime, T prime, T prime. Okay? So if I were to write this in index notation, it would look like that. And where this is sort of a shorthand for that kind of partial derivative, and this is a shorthand again for the partial derivative, and then this gives the inverse Lorentz transformation. So this object, it's a 4-component object, but doesn't transform quite like a 4-vector because it's a covector. This is what we call a covector, with transforming with that inverse transformation instead of the forward transformation. So that's a covector. So if I look at the gradient of a covector, a gradient of a 4-vector, so I'm going to do the same thing, but this is no longer a scalar, but actually a 4-vector itself. Then if this is how I transform the partial derivative using an inverse transformation. And then I need to use a forward transformation if I'm going to a new reference frame for the 4-vector components. So our ordinary Lorentz transformation. And so the transformation of this 16-component object there involves one inverse transformation and one ordinary transformation. And that thing is a tensor. Okay? And a tensor is simply a set of components that transforms in a certain way. An upper index transforms with a forward Lorentz transformation. A lower index transforms with the reverse transformation, the inverse transformation. And that's why the upper and lower indexes are important. They tell you what kind of transformation you need to use. All right? So a general tensor transformation, you can have whole bunches of upstairs and downstairs coordinates. And for every upstairs coordinate, you have a forward transformation. For every downstairs one, you have an inverse transformation. That's the definition of a tensor transformation rule. All right. And let's look at, so here are some things that you can do with tensors that are still tensors. Here is a tensor product where I just sort of bump these four vectors together. And so the time component of this tensor is this 4 vectors time component times this 4 vectors time component. If I want the tx component, then it would be this one's time component times this one's x component, etc., etc. Okay, so there's 16 combinations, so this is a 16 component object. And if you look at how it transforms, both of those 4 vectors transform according to the forward Lorentz transformation. And so that is, by definition, a tensor with 2 upper indices. Transforms like a tensor with 2 upper indices, right? So if I contract over a tensor's indexes, so say I have a tensor with 1 upper and 1 lower index, and I sum over those indices, then that's really, if you think of this as a matrix, that's going to be summing down the diagonal of the matrix, the TT and XX and YY and ZZ component. So it'll just be a number. And how does that transform? Well, the upper index transforms the lower index transforms the inverse, upper index transforms as a forward. And if you bring those together, what's this product? The forward transformation times its inverse, summed over the alpha here. Yeah, it's the identity, Kronecker delta here. And if then I do a sum over that, then I just get a sum down the diagonal. So I've got something that's the same number in both frames. What kind of a quantity is that? Yeah, it's a Lorentz invariant scalar. So this is why we sum over upper and lower indices. And just upper and lower indices. If I did sum over 2 indices that were both lower, or 2 indices that were both upper, I'd get nonsense. I wouldn't get a number that would actually be a frame-independent number. But the summing over an upper-lower index does give you a frame-independent number. Okay? So, the metric, that metric thing that I described is in fact a tensor. I'm not going to go over the proof because I'm way out of time. But I sort of wanted to end with, here are various tensor operations that we can do. So one thing that's important for what's going to go on is to define the inverse metric, which is simply the matrix inverse of the ordinary metric. And guess what? You can sort of do this calculation in your head. What is the matrix inverse? Well, it's the same thing. In terms of the components, the upstairs metric, it looks just like the downstairs metric. That's not true in general relativity, but it is true in special relativity. So this thing has the same components, but it does transform like a tensor with 2 upstairs components. And so one thing that you can do is lower indices using the metric. If I've got a 4 vector, I can convert it into a covector. And you can show that this has the right transformation properties for a covector. If I have a covector, I can raise the indices with the inverse metric. That's an operation that converts a covector to a vector. I can add these As long as the indexes are the same and in the same position, the transformation, the sum will be that of an ordinary vector. So addition. So here are things that we can do with tensors. Add them, as long as they have the same number of indices in the same position. I can take a tensor product, and that's just going to create a larger tensor object. I can contract. And why is the Kronecker delta contracted with itself 4? Isn't it 1? Yeah. So what are we doing? Kronecker delta is equal to 1 whenever the indices are the same, but I've got an implicit sum here. So I'm summing down the diagonal of the identity matrix, and in 4 dimensions that yields 4. Okay? But my students always are blown away by that. They always write that it's equal to 1, but it's equal to 4. Okay? I can lower indices, I can raise indices, and I can rename summed indices, because summed index names are completely arbitrary. All right? So why tensors? A tensor equation is absolute. You write it once in one reference frame. If it's true in one reference frame, it's true in every reference frame, because the tensor transformation rule means that if these two vectors are equal in one reference frame and I look at them in a different reference frame, they're still equal because they transform alike. Okay, so here is an example of a tensor equation which basically says I take the magnitude of the 4 momentum, which is the negative mass squared, and that derivative ought to be 0. And it doesn't matter what coordinate system you use. That derivative will be 0 in any coordinate system, because the magnitude of the 4 momentum is frame independent. And that's what that equation says. And that is true no matter what coordinate system you use. All right? So the very last thing that I want to so let me just leave you with some terminology that I think will be helpful as we go on. So this is a free index. Its value can freely take on any one of the 4 values, tx, y, z. Okay? This is a bound index. You're summing over it. So it takes on all 4 of those values, and you're summing over the value. And so a free index tells you how many equations you have. If you've got a free index, you've got 4 implicit equations, one equation corresponding to each value of the index. And you're summing over 4, so each of these equations has 4 terms. And so in an equation like this, where there are, I call these terms, and these are factors in the terms. So this is a factor and this is a factor. You can rearrange those factors in any way you want. Doesn't matter. It's commutative, unlike matrix notation, because the sums are indicated differently. The sums remain the same no matter how you rearrange the terms. And so the factors you can rearrange, and in the 2 terms we can have some other freedom. So the rules are about, and these rules I think are worth keeping in mind. My students have lots of trouble with these rules. So you can't, when talking about free indices, you can't add or equate items with different numbers or positions of free indices. Doesn't make any sense. Free index names must agree. So This equation is crazy. This equation is crazy. Look okay, maybe, but that equation's crazy. Wrong positions, right? Those are not equal by any means. This equation is crazy because this has a whole bunch of free indices and this side doesn't. Okay? The only exception is 0 can have as many indices as you like. Right? And that's because the 0 tensor, no matter how many components it has, always transforms to the 0 tensor because the transformation's linear. Okay? So renaming free indices, this is important. You can rename a free index with a different index name as long as the name doesn't collide with any other free index name or any bound index name, and you can rename every occurrence of that index name. So this is bad. So I'm renaming this index. What did I do? Why did I make it? Why did I screw it up? Yeah, I need to change that out. This, if I'm going to change mu, I got to change it in both places. Right? Why is this bad? So I'm changing here and I'm changing here. Yeah. Yeah, what's going on there? Golly. That looks good. Why did I say it was bad? I must have had another example in mind. Okay, that one's good. What's wrong with this one? What's wrong with that one? Yeah, I renamed this mu index so it collides with this other summed index. So am I summing over mu or am I not summing over mu? I can't tell here. This is confusing. So don't do that. All right. So renaming bound indices. You can rename a bound index that is a summed index as long as it doesn't collide with any free index name or any bound index name in the same term. And you rename both occurrences. So here it's bad because what did I do? I renamed this mu to this nu to mu. And why was that bad? Yeah. So am I summing over mu or not summing over mu? It's hard to tell. But on the other hand, this can be really an advantageous tool if I want to do the tensor transformation. Usually, habitually, when I do these kinds of things and this sum is distinct from this sum, I give them different names to indicate, yeah, I'm thinking that they're distinct. But this bound index is in a different term than this bound index. So I'm totally free to name it whatever I want as long as I don't name it mu. Okay? So I'll rename it nu, and then I can pull the common term out in front and show that this is in fact, this sum obeys the tensor transformation rule. So it's very helpful to rename bound indices sometimes as long as you do it right. All right? And, oh yes, fourth rule. When in doubt, write it out. In other words, write out the sum explicitly to see whether it's legal or not, or to see what you think the sum means. All right? So, there is an exercise here, but since I've gone way over time, I'm going to leave that with you, and I'm happy to talk with you if you want to sit here and ponder it. But if you need to take a break, I think we're going to have the next talk at 11, right? Okay, so thank you very much for your attention so far. And there's more actually on this. Oh, the very last thing I was going to do was show how you could use all this tensor stuff to derive Maxwell's equations. But it's there. Okay, so go check it out. It's really cool that you can do this. You can just take Gauss's law and the Lorentz force equation, well, the definition of electric field, basically, how the electric field creates a force. Take those two equations, make them tensor equations, and wow, Maxwell's equations just pops right out. And you could have discovered magnetism if we hadn't known about it. You could have discovered it that way. It would have been so cool. Nobel Prize for sure. All right. Anyway, thank you all for your attention. Appreciate it.